Hello everybody, what we are going to be doing today is solving a system of equations. So you can open up your green packet, and what you can do is you can turn towards the page that says solving systems of equations. And so as you go through this, you can pause it if you need to, you can rewind, whatever have you. But what I'm going to do is just kind of lead us through this next topic. And one thing to bear in mind as we do this, we're going to practice it some more. So if we don't quite catch what's going on, this isn't going to be the first day that we go over it. But first and foremost, as we fill this out, what we're going to do is we're going to solve a system of equations. And so this word system or systems implies that it is a set of two or more lines. And so what we are looking at is, for example, two lines where we would be given something like this: y equals 3x plus 7 and y equals negative 2x plus 2. Okay, so for example, that would be two lines. And what we are trying to do is I'm trying to determine where is it that these two lines intersect. So for example, this line here has a positive slope, so it would be increasing, and so it would be something like that. And the second line, this one here is one has negative slope. I'm not putting it on a set of an XY axes, but that line would be decreasing, and these two things intersect or cross each other at some point right here. And this is the answer that we're going to learn how to solve with algebra. We're not going to look at the graph necessarily. What we're going to do is try and solve that algebraically. And this is a point on the graph where they cross each other. That has an x and a y coordinate. And so the answer to solving a system of equations is always written as an ordered, that's what this word is going to be, ordered pair. And when we say ordered pair, that's x comma y. And this is the point on the graph where the two lines intersect. And I just demonstrated that up above. So when we go through and we try and identify how to solve this, there are three different methods that we are going to use to solve these systems of equations. One of them, which we can practice on Monday or the next time that we gather together, is going to be done by graphing. So what I'm going to do now is move down to this next section and just detail the three different ways that we can solve a system of equations. We can solve one by graphing, all right? And what that means is the following. We are going to graph, we're going to graph both lines and see where they intersect. And so one word that I need to make here is that this is not always accurate, or not always the most accurate. And the reason is because you're kind of estimating on the graph where these are going to be intersecting or where they're going to cross. And if you're not super precise, you might be off with that. So we're not going to do tons of graphing to see where two systems or two equations rather intersect. What we will do is do something like substitution. That's the second method that we will use or employ, and this involves algebra. And what we're going to do with substitution is the following. We are going to use this method when both or one equation is solved for a variable. So what do I mean by that? Well, if I give you a system of equations that looks like the following. Notice in this instance, I have a system of equations. I have two equations, yet this top one looks different than the bottom one. The top equation is solved for a variable. What do I mean when I say it's solved for a variable? Notice that x is all by itself. And so there's nothing next to the x. It says x equals. So it might be worth noting that this equation right here is solved for x. And so what we end up doing then, whatever is solved for a specific variable, is we take that quantity and we eventually are going to substitute it. So in this case, 3y plus 7 in for x in the bottom equation. And I'll go through an example demonstrating that in a little bit. But substitution would be the second method that we could use to solve a system of equations. And thirdly, the third one that we're going to employ is what we refer to as elimination. And so substitution and elimination both use algebra. And elimination is another one that you might have seen before, just like substitution. So what is elimination, or when would we use that? We would use this method when both equations have x and y on the same side. So I'll draw an example here in a moment what that looks like, but we use that method when both equations have x and y on the same side. So something like the following. So you'll notice here in this particular case that both x and y are on the same side of the equal sign. And so that way we can go through this method called elimination. We need both of those to be on the same side. And so unlike up above, up here, x and y, and both equations are by themselves, the numbers on the other side of the equal sign have no variables next to them. So that's kind of the first page. What you're going to do is you're going to flip to the next page, and we're going to work through a couple of examples just to see if we have an understanding for this all together. So hopefully you've flipped over to the second page now, and what we're going to do is we're going to look at the following example. Write down what I put down here. So what you'll note here is that we are trying to solve this system of equations, and so we refer to this as a system of equations because there are two lines that are being shown to us. And so what we first need to identify in solving this is which method should I use. And if you look back to the previous page, we have graphing, substitution, and elimination. And so in this particular case, what I need to identify is that I have this top equation right here that is solved for a variable. This top equation is solved for y, and that indicates to me then that we are going to use substitution in order to solve this. And so by using substitution, what I'm going to do is I'm eventually going to replace something in the bottom equation with what y is equal to, but using substitution because y is solved for. And so using substitution then tells me that I'm going to substitute y equals 6x minus 11 in for y in the bottom equation. And that's going to look something like the following. So hopefully you can notice here that I took the bottom equation, which was negative 2x minus 3y equals negative 7, and instead of writing y, I now wrote what y was equal to from the first equation, which was 6x minus 11. And hopefully we can recognize it as at this point that I have one variable. I only have an x left. And so what we're going to do then from this point is we're going to solve this equation for x. And we practiced this skill the other day. I'm going to pause the video, And what you should do at this point is try and isolate x. Get rid of the parentheses and solve this equation for x and see what we end up with. All right, so hopefully you've gotten to the point where you were able to solve and you'd find out that x is equal to 2 after distributing. Make sure that when you do -3 times -11, that makes +33. And solving that, I get x equals 2. Now here's the catch. When we're solving a system of equations, we're not done once we find what x is equal to. And so something that bears worth writing down is that after you find what x equals, okay, so whatever x or y, what we need to do is we also need to find what y is equal to. So you solve for both x and y when we do this. And in order to do that, what we're going to do is we are going to plug x equals 2 back into the original equation. And the question is, well, which one? I'm going to choose the top equation to plug it back into. And the reason being is because y is already solved for a variable. I know that y is equal to 6x minus 11. And we just found that x equals 2. And since x equals 2, what I can then do at that point is I can take this value of x equals 2, put it in right here for x. And so my work then is going to look like the following. I'm not going to write with a highlighter, but rather I'm going to write with the pen. We're going to get y equals 6 times 2 minus 11, which is y equals 12 minus 11. And then we get y equals 1. And so at the end of the day, when I solved, I got x equals 2, y equals 1. And to finalize our answer, we always write it as an ordered pair. So remember, that's written as x comma y. So I'm going to write my answer as 2 comma 1. And that's going to be my final answer. That's what it's going to look like in that instance. It's 2 comma 1. So that's the first example using substitution. What we're going to do is go down to where it says number 3, just kind of in that spot. The numbers don't really matter, and we're going to do one more example. All right, so what we have down here is we have an equation, and actually 2 equations. And what we'll notice in this case is that x and y are on both sides of the equation. All right, I have x, y, they're both on the left side, and there's nothing with a variable on the right side. So this tells us in this particular instance that we are going to use elimination. And what elimination is it's trying to get rid of a variable by adding the 2 equations. And so what I'm going to do, and what I would encourage you to do right now, is let's draw a line underneath here and slap a big plus sign. And what's going to happen is we are going to add all of the like terms together. So we're going to add vertically. And so what that means is I'm going to add 3x and x together, and that makes 4x. Then what also I can do is I can add these 2 together, and this is the point of elimination. When I add -4y and 4y, those just cancel out, hence they are eliminated. And then when I add 10 plus -2, that's going to make 8. And so now I have an equation with no more y's available. And so they're all gone. And so now I can just go about solving this like I normally would. I'm going to divide both sides by 4. And when I divide both sides by 4, that's going to yield x equals 2. So I solved for x by using the elimination method. I noticed that I had opposite coefficients or opposite numbers by the y's. And so I added those 2 equations together. The y's went away. So my last step then, just like what we did before, is we need to plug x equals 2 into either equation that we started with to solve for y. And so that work then is going to look like the following. I'm going to plug it into the bottom equation because there's not as much stuff going on there. So you can see here I have 2 plus 4y equals -2. And it's in this instance I'm going to subtract 2 from both sides, and so I am again balancing this equation. I'm trying to solve for y, and in doing so, I'm left with 4y equals -2 minus 2 is -4. And so my last step, I can divide both sides by 4. And in doing that, I'm going to get that those cancel away and y equals -1. And so I now found what the y value is for this point on the graph where they cross. And so this then means that I'm going to have the point 2, -1 as my final answer. And so this is again how we record it, 2, -1. And so finally, down here at the bottom, and we'll talk more about this at a later date, if the system has two lines that are parallel, and remember that word parallel, it's probably worth writing down here on the bottom. It means that they have the same slope. So if two lines have the same slope or they're parallel, we say that the system has no solution. And the reason for that, what you'll find out when you try and solve that, you have two lines that are going like this. They actually never cross one another. And so therefore, their lines are never going to cross, and there's no point of intersection, so there's no solution. So if they have the same slope, we say that the system has parallel lines, and there's no solution. And lastly, if the system has two of the same lines, so if you have same line on top, same line on bottom, we say that there are what we call infinite solutions. I hope this was helpful in getting it all down. We'll touch base at a later date to try and make sure that we enhance these skills all the more. Otherwise, thanks for your attentiveness, and we'll work with this soon.